All right, this will be the transformations of the graphs for the y equals sine of x or y equals cosine of x. Okay, I just use x for the angle instead of the Greek letter theta, just because that's what we're used to when we do the transformations. All right, so it's basically the same thing we've learned in the past. All right, if you want to shift up or down, you just add or subtract from the original function. All right, so this could be sine or cosine, but if the original function was the sine of x and you did plus c, that moves it up c units. Okay, and if you start with sine of x and you do minus c, that makes it move down c units. Okay, so it's the same thing as we've done in the past. You add or subtract from the original function and it moves it up or down that many units. Now, if you multiply a number times the original function, let's say you once again start with sine of x or cosine of x, and you multiply it by a constant term a. If the absolute value of a is greater than 1, that's a vertical stretch. Okay, in other words, if you multiply by, let's say, the number 2 or negative 2, it's going to stretch the function vertically. It's going to make it elongated from top to bottom. If the absolute value of a is in between 0 and 1, that's going to be a vertically compressed. So in other words, if this is a fraction between 0 and 1, whether it's positive or negative, it's going to compress it vertically. It's going to make it shorter from top to bottom. And finally, shifting left or right, remember it is the opposite. Okay, so if you do minus b, if you subtract b from x, that moves it to the right b units. Okay, and if you add b to x, that moves it left b units. So remember, for left, right, it's opposite. When you go negative, when you subtract from x, it goes right. When you add to x, it goes left. Okay, and notice we are adding and subtracting inside the parentheses because there's a difference between adding or subtracting from x and adding or subtracting from the original function. Okay, so if you do plus or minus c to the entire function, that moves it up or down. But if you just add or subtract from x, that moves it right or left. All right, let's look at some examples. The dashed graph is one period of f of x equals sine of x. Is same thing, y equals sine of x. And the solid graph is the transformation. Match the equations below with their graphs. All right, so remember, for these, the dashed line is the original, y equals sine of x. The solid line is going to be the transformation. All right, and the equations to choose from are these equations right here. I am going to try to write each one before looking at the choices. All right, so let's start with figure 1315. All right, 1315, the dashed line is the original. The solid line is the transformation. So let's see. Notice the original, the maximum is at 1, and the minimum is at -1. Now, if you see the transformation in the solid line, the maximum is at 2, and the minimum is at -2. So what happened here? Well, this was basically multiplied by 2. All right, that's a vertical stretch. That's a vertical stretch, and it's going to be times 2. All right, so we'll keep that in mind. And let's see what else we have here. All right, notice the original one starts at 0, whereas the transformation one starts here. All right, so it seems to be about halfway between 0 and pi over 2. See, this point right here is pi over 2. This is 0. So what's this point right here? I say that's halfway between pi over 2 and 0. So basically, what's half of pi over 2? Well, that's just pi over 4. All right, so this point right here is pi over 4. Okay, that means it shifted right by pi over 4. All right, so it shifted right by pi over 4. Now, it doesn't look like it was shifted up or down at all. It was vertically stretched, but if you look at the middle, of both graphs, right, this one, the max is at 2 and the minimum's at -2. So the middle, or the midline, is right here at 0, the x-axis. And if you look at this graph right here, same thing. It goes from 1 to -1. So the middle of the graph is right here. So it was not shifted up or down at all. So these are the only transformations. All right, so if you start with y equals sine of x, and you vertically stretch it, that means you multiply it by 2. So that's going to be 2 times the sine of x. Okay, that's a vertical stretch. And if you go right by pi over 4 units, remember left, right is opposite. So to go right by pi over 4, it's going to be minus pi over 4. All right, so that is the equation for figure 1315. All right, so 2 sine of x, x minus pi over 4. That is 1315. All right, let's look at 1315. This one right here. That's going to be figure 1315. All right, 1316. Let's see, what is the vertical stretch? Again, the original is in dash. It goes from 1, and the minimum is at -1. And look at the new one. The maximum is at 3, and the minimum is at -3. So how much is the vertical stretch? All right, the vertical stretch is times 3. Now let's look at the shift. Okay, this is the original. It starts at 0. The new graph, the solid one, starts here at -pi over 3. So basically, it shifts left by pi over 3. See, this is -pi over 3 right here, this dot, that point. All right, so left, I'll just write LT, left by pi over 3. All right, see if you can write the equation. Start with the original sine function, sine of x, and see if you can write the equation, please. All right, vertical stretch times 3. We're going to multiply it by 3. And it shifts left by pi over 3. So in other words, it's going to be plus pi over 3. When you go left, you add. All right, so we need to look for this function, 3 sine of x plus pi over 3. And that's going to be 1316. Okay, right here, this is 13.16. All right, please pause and see if you can do this one here. All right, so the dashed line is the original. It runs from a maximum of 1 to a minimum of -1. Here is the new one, the solid one. It runs from 0.5 to -0.5. So that is, instead of vertical stretch, it's vertically compressed. All right, and it's going to be times 1/2 or 0.5, same thing. And now let's look at the shift. All right, the dashed line starts at 0. The solid one starts at -2 over pi, -pi over 2, so it shifts left by pi over 2. All right, so that shifts left by pi over 2. All right, so start with the original. Y equals sine of x. The vertical compression is times 1/2. and it goes left by pi over 2, which means you are adding. Remember, it's opposite for left, right. You are adding pi over 2. So it's 1/2 sine of x plus pi over 2. That's 13/17. All right, 1/2 sine of x plus pi over 2. That's going to be 13/17. All right, last one. See if you can write the equation for this one, please. All right, as always, the original sine function, it runs from a maximum. It runs from a maximum of 1 to a minimum of -1. This new function in the solid line, it runs from max of 3 to a minimum of -3. All right, so the vertical stretch is going to be times 3. And now let's look at the shift. All right, the original starts at 0. The new one starts right here, okay? That point is in between 0 and pi over 3. It's halfway. It's halfway from 0 to pi over 3. All right, so basically half of pi over 3 is going to be pi over 6. It basically moves to the right by pi over 6. All right, it moves to the right by pi over 6. All right, so as always, you start with your original sine function. Y equals sine of x. It's times 3 because it's a vertical stretch of 3, and it goes right by pi over 6. That means, let me rewrite, y equals 3 times sine of x. It goes right by pi over 6. That means you subtract pi over 6, because when it goes right, you subtract. So that's it, 3 sine of x minus pi over 6. So that was the last one, I think. That was 13.18. Figure 13.18. All right, so we did all 4.